Okay, so today we're going to talk about power, right? Which we don't really need to know a whole lot about. We just have to understand what it is and what things might affect it. Okay, you won't be asked to do any calculations to do with power. Okay, although I'll show you a couple just so you kind of understand how they work, but you won't be asked to repeat that. Okay? It's a pretty short and straightforward idea. Okay, so we need to understand what power is, understand the relationship between power, force, and velocity, and we need to understand or learn that power relates to how quickly work can be done, not how much work is done. Okay, it is key that we understand that. Okay, that power is the rate at which we do work, not how much we do it. Okay, all right. So if I compare these two 1997 Honda Civics, okay, the one on the left is the stock version that you could buy in 1997. It had about 85 horsepower, top speed of about 130 kilometers an hour downhill with the wind. Okay, it was not a very fast car. Okay, but if you give it to Paul Walker and Vin Diesel, and they do that to it, okay, it will be much more powerful. Okay, they will put, you know, turbo on there, cold air intake, pilot cannons, pistons, you know, stuff like that. Fun stuff that makes it more powerful. Okay, and as a result, it would be able to go, okay, from 0 to 60 in about 4 seconds, whereas this one would do it in about 2 weeks. Okay, because it was not very powerful. Okay, so can they both get to 60 miles an hour? Okay, that requires the same amount of work. Okay, they're essentially the same car. Okay, but one can do it faster, and that's the key thing about power. Okay, a more powerful machine is yes, capable of doing more work in a shorter time. Okay, but when it comes right down to it, they can both do the same amount of work. One just does it faster. Okay, I think yesterday the examples I used were like a microwave and a hair dryer. Okay, pretty standard things that we use every day. Okay, if I have a 900 watt hair dryer and a 1600 watt hair dryer, the 1600 watt hair dryer is going to dry my hair pretty quickly. Well, actually they both will because they don't have very much left, but okay, one will do it faster than the other simply because it's more powerful. Okay, everybody all right with that? Okay, now the units in the metric system for power are watts. Okay, and a watt is a joule per second. Oh, is that a terrible color to use? Let's try that instead. That's probably better. Okay, so a watt is a joule per second. Okay, in other words, it's work divided by time. Okay, that's how we would calculate power. Now, the two things you see on the screen there both do the same thing. They convert the mechanical energy of falling water into electricity. Okay? The one on the left, that little water wheel, probably generates enough electricity to run a couple of light bulbs. The one on the right, Grand Coulee Dam, supplies electricity to the Pacific Northwest. Okay? That would be Spokane, Coeur d'Alene, big cities. Okay? Basically all of like Washington and part of Oregon. Right? It's a pretty big thing, right? Now, could they do the same amount of work? Absolutely. If I ran Grand Coulee Dam for 1 second and that water wheel for 200 years, they'd probably do the same amount of work. Okay? It's not practical to do that. Obviously, more powerful things are going to do more work in a shorter period of time. Okay? All right. So it's the idea of power is simply the amount of work done per time interval. Okay? So when we look at the formula, power is work divided by time. There's actually different manipulations of that. Since we know that work is force times distance, okay, we can say it's also force times distance over time. Or we can say that since distance over time is average velocity, we could also just go force times average velocity. Any one of those would calculate the work. Okay? There's lots of different formulas. Again, I'm never going to ask you to calculate anything on a test, okay? But there's lots of different ways to do it. Okay, now, I don't know about you, but watts is not something like I understand it when it's small things, okay, like a 60-watt light bulb. I understand kind of how much power that is. But when we start getting into the power rating for much larger things, like cars, for example, okay, if you go up and you now look at, like, if you're buying a hybrid, a plug-in hybrid car or an electric car, the power is not in horsepower, it's in watts. And it kind of becomes a strange exercise in figuring out how powerful that thing is, okay? Because, I look at it, it's like, it's 20 kilowatts. I'm like, is that good? Because I really don't know. Okay, like I can understand that, yeah, my blender is 1,000 watts, and that's, does a good job of pulverizing things, but is 200 times that or 20 times that a lot? I don't know. Okay, it's hard to figure that out. So to tell you, just so you have an idea, 1 horsepower, which is something that's a bit more meaningful. When I walk up to a car, I want to know how many ponies are under the hood. Okay, 1 horsepower is 746 watts. Okay. So, if you ever wanted to do the conversion, okay, that means that 1 horse on a treadmill could generate enough electricity to run 7 100-watt light bulbs and like 1 40-watt light bulb, okay, all at once. Somehow diminishes a horse's power, but okay, that's what 1 horsepower is. Okay, now how do they figure that out? They attach a horse to a weight hung over a pulley, and if it can pull it at 1 meter per second, force times velocity, okay? There's 746 newtons there, okay? And it can pull it at 1 meter per second, okay? That sort of makes sense? That's kind of how they determine power. Okay, since we don't have to do calculations, we're going to skip that, okay? And that's all calculating. And we're going to move on to this, because it's more fun. Okay. We're going to figure out how much power Yoda can generate. Okay. So, the idea behind this was that at one point somebody had come up with this like theoretical paper about how you could use Superman to generate enough electricity to power the entire world, but that was somehow wrong because it would be enslaving him or something like that. Okay, so this guy got, because I didn't make this up, I'm a nerd, but this is a whole other level of nerdiness, okay, figure out. So, we're gonna figure it out. So let's imagine we put Yoda, down at Pincher Creek by the wind turbines, okay? We wanna generate some electricity, but it's not a windy day, okay? And so we put Yoda down there and, he does his thing and he'll be like, rotate your wheel. And we'll get them going, okay? And we'll make some electricity. All right, so how many people have seen the Star Wars movies? And by the Star Wars movies, I mean episodes 1 through 6. I don't mean the other ones, because they suck. I won't rant about that, because that'll take a whole other class, okay? So we're gonna look at one particular scene from the greatest movie ever made, The Empire Strikes Back. Okay? This is the first time that the Force is ever explained to us. Okay? And what it is and how it works. Okay? And Yoda tells Luke all about it. And then he tells Luke he needs to lift his spacecraft out of the swamp. And Luke, of course, fails because he tries. Okay? What does Yoda tell him? There is no try. Okay? He says, try not, do or do not. There is no try. Okay? So what we're going to look at is, after that, obviously Yoda does it for himself. He's like, punk. I'll take it out myself then. Okay? So what we're going to look at is that scene. Okay? So I'll play that scene first, and then we'll go from there. Okay. Turn that light back on for me, please. All right. So there's a good life lesson in that. Okay? It's important. It's all about like, if you believe in something, it can happen. Okay? It's about like the difference between faith and certainty. Okay? Luke was certain he couldn't lift the ship, so he tried. Okay? But he was certain he couldn't lift it because it was too big. Okay? Whereas Yoda believed he could, and so he did. Okay? So the difference between faith and certainty. Okay? Certainty is easy, faith is hard, okay? Because there's nothing to prove what you believe, okay? That's what makes it difficult. All right, so Yoda's greatest display of raw power in the original trilogy came when he lifted Luke's X-Wing from the swamp. As far as physically moving objects around goes, this was easily the biggest expenditure of energy through the Force we saw. Okay, so can we calculate the energy it would take to lift Luke's X-Wing? Right, be the work done, okay, the amount of potential energy it would gain. Agreed? Okay, what things do we need to calculate that? All right, we need the object's mass. Okay, so that would go here. Okay, we would need gravity. Okay, and height. Okay, so this is going to be a little bit problematic. This doesn't happen on Earth, it happens on Dagobah. I have no idea how heavy an X-Wing fighter is, okay? Nor do I really know how high he lifted the thing, but that's okay. There are people out there far nerdier than I. Okay? So, we need to know how heavy the ship was. The X-Wing's mass has never been canonically established. That means it's not in Star Wars canon, which is what Disney says is true. Okay? So, but its length is 12.5 meters. For some reason, that has been. Okay? So, an F-22, which is a real aircraft, is 19 meters long, weighs 19,700 kilograms. So if we scale it back, the X-Wing's about 12,000. Sorry, that's supposed to be kilograms. Okay? There. All right, so we've got that. Okay, then we got to figure out, 5,600 kilograms. Sorry, 5,600 kilograms. Now we need to know how fast it was rising. So this guy sat down and pored over that same clip for a very long time, okay? And also a few other shots from other Star Wars movies so that he could figure out how tall the landing gear was. Okay? Because in A New Hope, the movie before this one, okay, there is a shot of someone ducking underneath the X-Wing fighter and his shoulder just brushes the nose, which means that in this stooped position, he would have been the same height as the landing gear. Okay? So from there, we're going to assume that the landing gear is about 1.4 meters long. Are you getting like the level of like obsession that people might have here? Okay? All right, and then he timed it because we need to know how fast it was coming out of the water so that we could get the speed at which it came out of the water. Okay, so it is 1.4 meters long, and it was coming out of there. No, where did he give us the time? Oh, I lost something there. 3.5 seconds. Sorry, wrote it out in words. That's why I didn't find it. Okay, so it takes 3.5 seconds for it to travel 1.4 meters. Can we figure out how fast it's going? Okay, so we just go 1.4 over 3.5. Someone punch it in the calculator. It's going to take forever to fire up. What is it? Point 0.4. Okay, 0.4 meters per second. Okay, and then lastly, we need to know the strength of gravity on Dagobah. Yeah, right. Somehow we're going to get that. Yes, we are, because there's this thing called Wikipedia. It's a real thing. Okay, yeah. Wookiees are like Chewbacca, right? And so there is a catalog of all sorts of little pieces of information. And they find out that the surface gravity on Dagobah is 0.9 g, which means the g on Dagobah is 0.9 times 9.81. So you'd be a little lighter on this planet. All right, so now we have the gravitational acceleration of Dagobah, 8.829 meters per second squared. All right, so now we should be able to figure out the amount of work that was done by Yoda. Okay, so we can go m times g times h. Okay, so when we do that, we'll take our 5,600 kilograms, we'll multiply it by 8.829, and we'll multiply it by 1.4 meters. Okay. Okay, that's how much much work he did. Power is work divided by time. Okay, so 19,776 watts, so roughly 20 kilowatts worth of power. Okay, so that's enough to power a block of suburban homes, so like your neighborhood. Okay, that's about it. Okay, it is about the power of the motor in an electric model smart car, which somehow greatly diminishes what Yoda is capable of. Let's put it that way. Okay, so at current electricity prices, Yoda would be worth about $2 an hour. That sucks. Minimum wage is what, 15? Okay. Ouch. Okay, poor little guy. It ain't easy being green. All right. Now, we know that obviously there's other things that we see in the movies, like people zapping people with lightning that comes out of their fingers, which looks really cool, but it's pretty far-fetched because the amount of power needed to do that, to arc electricity like that, especially over great distances, is beyond unimaginable. Okay, so that would be a lot greater use of force power in order to do that. Okay, so it's not great. We'd need a lot of Yodas in order to generate any significant amount of electricity, but at least it'd be green. It's terrible. Okay. That's it for power. That's all we need to know about power. I just wanted to have a little fun. Okay. So let's have a look at if there was anything else you guys wanted to ask about for the unit exam review. Because I feel like we kind of ran out of time yesterday. You guys were asking questions and we kind of ran out of time. So if you got any more, we got time.
Can you do a 2-box one with a string in the middle that's like being pulled?
Okay. Don't know that I have one like that on here. Okay. Okay, so these two boxes are attached to each other by a rope, okay, and there's a rope attached to the first box. 600 newtons worth of force is acting in that rope that is attached to the first box. There's 200 newtons of friction acting on box A. Okay, the boxes accelerate at 1.2 meters per second squared. I would like you to find the force of A on B. Okay, give you a few minutes to try that one. Okay. Which box am I going to use? Yeah, I have to use A. I know nothing about B. Okay, so let's just eliminate B for right now and just look at the free body diagram for A. Okay, we've got 600 newtons of pulling force acting on A. We've got 200 newtons worth of friction acting on A. And what else is acting on A? The force of B, right. Okay, that's the one that we sometimes forget. It's the easiest one to forget. Okay, force of B on A. what do I know about the force of B on A?
It's the same as the force of A on B.
Right, it's the action-reaction pair to the force of A on B. That means it's equal in magnitude, but opposite in direction. Okay, so if I can solve for that, then I have the force that B exerts on, or that A exerts on B. All right, can I calculate the net force acting on A? Yes, I can. I have its mass and its acceleration. So 75 times 1.2, all right, gives me 90. Oh, that worked out really well. It's almost like I picked it on purpose, but I didn't. Okay, 90 newtons is my net force, and that would be forward. Okay, and the other way to calculate F net is to add all of these things together, and I know 2 out of 3 of them. Okay, so that means F net equals the force of B on A plus the force applied plus the force of friction. Okay, so when I do this, okay, I'm simply going to bring force applied and force of friction over here by subtracting them. So I'll have F net minus the applied force minus the force of friction equals the force of B on A. All right, now I've got to put in the right signs though, because one of these is, well, 2 of these are backwards. Okay, so F net is forwards, so that's going to be positive. Okay, force applied, also forwards, so that's going to be positive. Force of friction is backwards, so that's got to be negative. Okay, and that should give me a negative number because the force that B exerts on A should also be backwards. Okay, everybody all right with that? Okay, so when I punch all that in, I should have 90 minus 600 minus negative 200. All right, so the force that A exerts on B is going to be 310 newtons forwards. Yeah. And we only have 2 significant digits, so 3.1 times 10 to the 2 newtons forward. Okay, everybody all right with that one? All right, when it comes right down to it, it's all Newton's second law until the very end when we go, oh, right, now it's the opposite force that goes the other way. Okay, all we have to remember about Newton's third law is that it's got action-reaction pairs. Okay, if I can find one side of the pair, then I know the other one. Okay, you're giving that a scowly look. What did we do?
No.
Okay. All right, what else? What else would we like to go over?
Can you do the one where there's 2 dogs pulling a bone or something, and it's on the
Okay. Exercise. Oh. Okay, give that one a try. Okay, so, I mean, the way we can start this is we can draw a free body diagram, just identify the forces. It's not gonna help us really get anything other than to identify the two forces. Okay, we've got a force this way, due west of 200 newtons, and we've got another force that is acting this way that is 150 newtons. Okay, so there's my free body diagram, but that won't help me get the final answer. What I need to get the final answer is a vector diagram, because the net force is the vector sum of all the forces acting on the box or exercise ball. Okay, so I'm going to take the 200 newtons due west, and then I'm going to put on the head of that, okay, the other vector, which was 30 degrees north of west, but shorter, 150 newtons, okay, which means that my net force is that line right there. And you can draw the box either direction, it doesn't matter. I'm just drawing it above so that it's out of the way and not overlapping. Okay, does it matter if you drew the 150 first and the 200 second? It doesn't matter either. Okay, either way it works. I just did it that way. Okay, so now I've got my vector diagram, okay, and now I need to find all my x's and y's, just like I would have with any other vector quantity. So green x is going to be the cos of 30, because it's the adjacent side, times 150. Okay, so 129.9 newtons west. Okay, y is going to be the sine of 30 times 150, which is going to be 75 newtons north. Okay. All right, and then obviously for my red vector, I've just got 200 newtons west. I don't have any y component on that one. All right, so now I can use those to get my purple x and purple y, my resultants x and y components. All right, so purple x is going to be 329.9 newtons, okay, west, and the y component is going to be 75 newtons. All right, now that I've got that, I can calculate the magnitude of F net. Okay, by doing Pythagorean theorem, so 329.9 squared plus 75 squared. Times 200. Okay, so okay, so we're looking at 338.32 as our net force. And we need the angle of that, because acceleration, which is what we're looking for, is a vector quantity. Okay, so we'll do tan of 329 over 75. All right, which will give us 77.19 degrees. That would be west of north. Of course, the complementary angle of 12.81 is also fine. Okay, but as long as it's north of west. And now I find the acceleration simply by going F net over mass. So our 338, okay, divided by 50 kilograms. All right, so we're looking at two significant digits, 6.8 meters per second squared at 77 degrees west of north, or at 13 degrees north of west, either one. Okay, so it's just a vector addition problem with an extra F net is m times a calculation at the end. Okay, no, you had one like that in the review package, so okay, it's just vector addition. You guys know how to do that. So. Okay, what else? What do you got? 8 minutes. Mm-hmm. Any other questions? What about a pulley question? I've never never asked a pulley question. Okay, the coefficient of friction between the 6 kilogram mass and the table is 0.252. Okay, there's a 4 kilogram mass hanging over the pulley. Calculate the acceleration of the 4 kilogram mass. Okay, let's have a look at this one. So, in this one here, we've got force of gravity, okay, acting down on the 4 kilogram mass. Okay, so 4 times 9.81, okay, 39.24 newtons. Okay, and we've got a force of friction resisting here that we'll have to calculate. The normal force for this will be equal to the force of gravity because there's no vertical forces acting on this box. Okay, so we just have to go 6 times 9.81. There's our normal force times 0.252. Okay, so 14.83 newtons. Okay, now I can simplify the diagram. Okay, 10 kilograms are being pulled this way by 39.24 newtons, resisted by 14.83 newtons. Okay, we find the net force. Okay, by taking that and subtracting that. Okay, there's our net force. We divide it by the mass, and we get that this is accelerating at, because we only have one significant digit, 2 meters per second squared down. Why can I write down? It's asking for the acceleration of the 4 kilogram mass. Okay, remember with system questions, it's about that all the parts accelerate at the same rate. Okay, Monday morning, you can start early, okay, on the test. So if you are here shortly after 8, okay, I will be here shortly after 8, and you can get started, okay. You only need to bring your pencil and your calculator, all right? I'll put the phones in the box, but you don't get your formula sheet. I put the formula sheet on the front of the test, okay? So you'll have that, not the one that you've written all over, okay? So just make sure you're here on time, ready to write, okay? If you normally write in learning support, your test is already there, okay? Just come and check in with me first, and then go there.